Physics time. We're going to do Newton's second law. Newton's second law. So as I said before, this should be a review. We're going to talk about it somewhat briefly. There will be some new information for you to write down. So basically, if you could remind me, as a statement, what is Newton's second law?
Acceleration of an object is dependent on two things.
It's a really good start. Acceleration of an object depends on two things. Acceleration of an object depends on two. You said variables. I'm going to put things, whatever. And what are those two things? First of all, we can say that acceleration, what do we use to abbreviate acceleration? A, specifically, A with an arrow, right? Because it's a vector. So acceleration, which is a vector, is we're going to say, what can we do to increase the acceleration of an object? If we want to increase acceleration, what else could we increase? We could increase the force acting on it, right? So acceleration is proportional. This little symbol means proportional. Acceleration is proportional to force, and we're going to specify force in two ways. First of all, force has to have also what? An arrow, because it's a vector quantity. And what kind of force is this true for? All forces cause acceleration? Oh, it's not called final. You already said it once. It's called the net. Someone said net. I can't tell you because you're all wearing masks. Net. So acceleration is proportional to net force. And this is directly proportional to. What's that mean? What's directly proportional mean?
Equally. If one increases, the other increases.
Right. As acceleration increases, force would increase by the same factor, or vice versa. Usually vice versa. As net force increases, acceleration increases by the same factor. They're directly proportional. We already know what else the acceleration depends on, but what is it? The object's mass, which relates to what other thing that we talked about in the last chapter. Mass and what else are not only proportional but the same. Those are proportional, but the object's mass and its inertia are the same. So really, we're saying that the more inertia an object has, the more or less acceleration it has. Less. So these things are inversely proportional. These are inversely proportional. Should mass have an arrow over it? No. Remember, we're really using this as inertia, but mass and inertia only depends on mass. So these acceleration and mass are inversely proportional, meaning that as mass increases, acceleration decreases. So altogether, we know, according to the second law, that acceleration depends on the net force and the mass, and they do that in this way. F sub net equals mass times acceleration. So basically, for a given force, if mass gets larger, acceleration must get smaller. And the reverse is true too. If acceleration gets larger, mass must get smaller. Almost always we're changing either force or mass to see the effect on acceleration, but that's not always the case. So those are the relationships among those things. Another part of Newton's second law is that the net force must be in. Sorry, I'm going to rephrase that. Let's start with acceleration. Acceleration occurs in the same direction as net force. They have to be in the exact same direction. Be very careful, because this is not the same as velocity. Can an object be moving, let's say, forward and accelerating backward? Yeah, what would that look like? Slowing down. So if it's moving forward but accelerating backward, what direction is the force acting on it? Backward. It must be backward, because force and acceleration have to be in the same direction. Does velocity have to be in the same direction as these two? No, but force and acceleration must be in the same direction. So if we have I guess ball. I was trying to think of a more exciting object than a ball. If we have a ball and it's in free fall, what force is acting on it? We'll say what two forces are acting on a ball in free fall. Gravity acting down always, F sub g, and air resistance acting up to some degree. We're going to make it significantly less than the force of gravity. But if we have a ball with gravity acting on it and air resistance acting on it, what is the net force on this ball? Well, they're supposed to be different lengths, so net force should be down somewhere, right? Some amount down. I don't know exactly what amount. If we put numbers with them, we could say this one's 5 and this one's 2, then our net force would be 3 down, right? But some amount down. Net force is down. So what direction must it be accelerating? Down. It has to be. Net force and acceleration have to be in the same direction. So if it has a net force down, then it must be accelerating down. Does that necessarily mean the ball is moving down? No, we said it's in free fall, so that does. But in the same way, if we threw a ball up, the net force on it is always down. And so it's always accelerating down. Throw the ball up and then it comes back down, right? If we throw the ball up, is it accelerating down when it's going up? Yeah, it's moving up, but it's still accelerating down. What does that mean it's doing? Slowing down. And then as it goes down, it must be doing what? Speeding up again, right? So that's how projectile motion relates to this. Please don't forget that this little bit is the thing that everyone, no, not everyone, but if you're going to forget something, in my experience, this is the part you forget. Net force and acceleration have to be in the same direction, even if velocity is in a different direction. I'm going to erase this real quick. We're going to start another topic. We have a couple other things to talk about, and this is all Newton's second law, right? So we're talking about Newton's second law. Looking at that equation, it's not going to be difficult for you to put math into it, right? So let's just do one of those real quick. Let's say, who wants to be in the example? No one? Let's put a freshman in it. What freshman should we put in the example? Can you guys think of a freshman? Lily. Okay, we'll have Lily. This is Lily. And she's going to be pushing a bulldozer. You know how she do. This is what a bulldozer looks like to me. Oh, they have tracks, don't they? Yeah, there we go. Now it looks like a bulldozer. Okay, so Lily is pushing a bulldozer. We'll say with a force of F net equals, we'll say 200 newtons. It's a children's bulldozer. F net equals 200 newtons, right? We'll say the mass of the bulldozer, M sub bulldozer, equals 13 kilograms. It's a very light children's bulldozer. Can we find the acceleration? What's the first step? I'm sorry, this should have an arrow. That should have an arrow. What's the first step? Which is? Let's memorize the easy one. To me, this is the easy one. F equals ma, right? Should be F net equals ma, but this is the easiest bit to memorize. F equals ma. It's also the easiest to manipulate because, as you can see, all of our manipulation can occur in one step. Whereas if we have memorized A equals F over m, it's fine, but if we ever want to find mass, we're going to have to do an extra step of manipulation. So F equals F equals ma. So we're trying to find what here? Acceleration, so we end up manipulating it. F over m equals a. Second step. Substitute. Tell me what to write.
Vector of A equals 200n over 13 kilograms.
Math? So math can be done. I should have picked an easier number than 13. 200 divided by 13 is going to be 18-ish?
15.3.
15.4 what?
Meters per second.
Meters per second squared. Remember, as a little aside over here, a Newton is equal to a kilogram meter per second squared. And so if we divide a Newton by a kilogram meter per second squared divided by kilogram, we end up with, well, look, meter per second squared. Right, so that's how the units work out in that. Questions about the math for this? This is fairly easy math, right? This is math that I was literally 25 minutes ago showing the 8th graders. This is not difficult math, but you can do it. I know you can do it. So, do you have questions about it though? It's okay if you have questions. Okay, let's move on then. So, another thing we're going to talk about is friction. Friction. I made my O look weird, but friction is the next thing we're going to talk about. There are lots of types of friction. One that we talk about a lot in here is air resistance. So write down that air resistance is a type of friction. There are other types of friction too, though. If someone, before you ever knew anything about physics, like before you took 8th grade, hopefully, if someone was talking about friction, what would that mean to you, generally? Usually two things rubbing together, right? You're doing the rubbing together hand thing. Friction usually to us means two things rubbing together. It happens whenever any objects move past each other or would move past each other. So friction occurs only when objects are in contact and it acts to oppose motion, or we say intended motion. Which means that, for instance, if you went to, unlike Lily's example with the children's bulldozer, if you went to push an actual bulldozer, the thing that would stop you from being able to actually move it would be friction. It's not in that case opposing motion because it's not moving, right? But it is opposing the intended motion. So basically, if this is you got string bean legs, and you're about to push this Big Daddy bulldozer. This is a really good drawing. I don't know what you guys are talking about. If you were going to push that, or you were going to try to push that, right, you would be applying some force to it. And basically, however much force you applied, even if it was very much, this is your push force, would be counteracted increasingly by the force of friction, which we usually abbreviate with that fancy little f, or at least I usually abbreviate with the fancy little f. Because it's not only resisting motion, it's resisting intended motion. It's preventing this object from moving. In this case, we call this static friction. When the object is staying put, in fact, stay, did I spell it wrong? I put too many I's in there. Stay and static have the same root word. Static friction is friction that prevents an object from moving, that stops it from moving. We also had, you wrote down air resistance, right? Is a type of friction. Air resistance is a type of friction that's in the subset of frictions that we call fluid friction. So since air is a fluid, what might be another example of fluid friction? Water. Yeah, that's why you can't, when you're trying to walk through the water, it's harder, right? Have you ever tried to jog through even a little bit of water? It makes it significantly harder because there's a lot more friction between your body and the water than there is between your body and air, which you normally jog through. Static friction is if the objects are staying put, and if the objects are moving, we call that kinetic friction. So if instead of pushing the bulldozer, you're instead pushing a toddler on a bicycle, oh golly, okay, that's a bike, I don't know, I'm going to give up on the bike right away. But if you are pushing them, first of all, in this case, what should be larger, the push force or the friction force? If they are moving.
Push.
The push force, you are pushing them, and so there's going to be a little bit of friction, but it's going to be smaller than the push force. So in this case, we call this kinetic or sometimes dynamic friction. And there are different, why can I not spell friction? And there are different kinds of kinetic friction. There's what we call sliding friction if they're sliding, and there's rolling friction if they're rolling. In this case, since it's a bike, well, since it's supposed to be a bike, it's rolling friction. All of these kinds of friction, static, dynamic, fluid, rolling, sliding, doesn't matter. All of them depend on two things. How could we, if we wanted to decrease the friction, like let's go back to the bulldozer example, if we wanted to decrease if we got to get this boulder out of here, what are the ways we could make the friction be lower? How can you decrease friction in general? What do you do if you want to decrease friction on a daily basis? What will have more, let me phrase it a different way. What's going to have more friction? If I try to push my little end table with my microphone across this carpet, What's going to have more friction?
Carpet.
The carpet. We know that instinctively, but why? What's different about the carpet? It's
It has more
Denser, right?
bumps.
yeah, it's bumpier, it's rougher. So the friction depends on these two things. Force of friction depends on, in the same way that we had, we did this for F equals ma, force of friction depends on two things. The roughness of the surfaces, which we call this. This is the Greek letter mu, and we call this is the coefficient of friction. This is a unitless number that you're either going to be given or you will look up on a table. It depends on the smoothness of both surfaces. Higher coefficients of friction are when rougher surfaces are touching. Lower coefficients of friction are when smoother surfaces are touching. The lower the coefficient of friction, the smaller the force of friction when those two objects are moving. It has no units, but it does affect the value. So thinking about that, what's one way we could make this bulldozer move? We could imagine if we had magical powers, what could we do to the surfaces to make it so it would move more easily? Make it smoother, right? If we could turn this ground, whatever the ground is here, to Teflon like your pans are made out of, right? And we made its tracks out of Teflon too, we probably could move it with our bare hands. Or if we made it ice, right? If we had this, you might even, I don't know how big bulldozers actually are. We're going to assume it's a little tiny boat, like a skid steer kind of deal. You could probably move a skid steer on the ice if it that sounds like a really dangerous thing to start doing, but you could probably move a skid steer on ice if you had to with your bare hands. I don't know. Because the coefficient of friction would be less. What's the other thing that the coefficient of friction, that the force of friction is going to depend on? What's going to be easier to move? There are my little end table here, which you can see on camera, good. Or if I started piling this up with stuff, like if I had someone come sit on this, would that make it harder or easier to move? Harder, which would mean it did what to the force of friction? Increased it. What has changed about it? Its mass changed, but that's not actually what matters for this. The objects, because think about it this way, even if it were massive, it has to be touching it. So if this were all happening in space, and we had a massive object on there, we could still move it almost as easily, because the friction wouldn't really be the problem. It's actually the force pushing these things together, right? Think about it this way. You did your little hand gesture for friction earlier. When you just rub them lightly, that's fine. If you really press them together, it's harder to rub them, right? So the other thing that the force of friction depends on is the force pushing the objects together. And we have a special name for that. Do you remember what it is? The force, we previously had said it's the force holding an object up, but it's the same thing as this. The force pushing objects together is called there's a hint. No, that would be F sub net. This is F sub n, which is the normal force. The normal force. It's the same force that resists gravity when an object is being held up. Our equation is this. F sub F, the force of friction, equals mu. I can't remember which side the tail is on, but one or the other. One of these is right. They're the opposite, and so one of them is right. You can look it up later. I think the tail is supposed to be longer on the right. Times the force, the normal force. So basically, the more force with which they're pushed together, the greater the friction will be. And also, the rougher the surface is, the greater the friction will be.
Is mu sub down?
No, it's just a letter. It's I would have like the alt code, but I can't. If you look up the letter mu on your computer, you can like highlight it and copy it and put it in your notes.
Okay, I was just wondering because I didn't know if it was sub like a.
No, it should be. We'll do some math with friction later on, but are you good with the concepts of friction now? What things impact friction? You know, you could tell me that, right? Okay. Let's move on to pressure. I'm going to go over here. This eraser's not doing such a hot job on this marker that was dying. Let's talk about pressure real quickly, because we have done this in the past as well. Pressure depends on two things too. The example I used to use for pressure, or I probably still do. The reason I say used to is because when you guys were freshmen, I used this. Those of you who were freshmen with me. If I apply the same force with each of these two objects on your skin, your flesh somewhere, right? Which one's going to hurt you more? The pencil, right? It's pokier. But the reason for that is that what you actually feel, what your body can detect, is not the force being applied to you, it's pressure. Your body has little cells that detect pressure. And so pressure depends not just on the force, depends on force. It does depend on how hard you press, right? That depends on the force, but also on what? Yeah, we just call it area, and sometimes we specify cross-sectional area. And it does it in this way. Pressure equals F divided by A. Where P is pressure. We'll talk about the units in a second. F is force measured in Newton. And A is, no, that's lowercase a. Capital A is area. And what would our SI unit for area be, do you reckon?
Something squared.
Something squared. What's our SI unit? What is it?
Meters.
Meters squared. Meters squared. So the unit for pressure is Newton per square meter, which is equal to a capital P lowercase a, which is a Pascal. Named after a man called Blaise Pascal, which is a pretty cool first name. So pressure is measured in pascals. There are lots of other units for pressure. This is the SI unit for pressure. It's really, really, really tiny because something with a force of 10 newtons is like, a newton is like 10 paper clips. That's not very much force, right? Covered over a square meter. Well, this is a meter. So this area squared with a force of about the weight of 10 paper clips acting on it is really, really not very much pressure, right? So a Pascal is very, very small. In fact, atmospheric pressure, just the pressure of the atmosphere pressing on you, is about 100,000 pascals. So this is a very small unit, but we still use it. This is the SI unit for pressure. This is the reason we watched a video, and you can look this up at home. But we watched a video on Thursday, I think, where they had the physics teacher lying on the bed of nails. Right, and they smashed his chest with a sledgehammer. You were all here for this, or I think you weren't here yet. But basically, he had this bed of nails here, and he was lying on it. And then they took another little bed of nails and put a cinder block on top. And then they had a sledgehammer smash this, and he was fine. Right, it's all nails. He's only laying on nails. But since there are so many of them, it evens out the pressure. Right, would this have worked if he was laying on one nail? No, it would have gone just through his body, right? So, like I said, in the same way that your body has cells that detected pressure instead of force, what can be deadly in a situation like this is pressure instead of force, right? I should have done this example a second ago, but you good on pressure? Let's return to air resistance in a falling object real quick here. I should have done this when we were talking about the ball a second ago, or 5 minutes ago. But imagine we have our ball again, right? When it starts its free fall, we are not negating air resistance, just like we did last time. When it starts its free fall, we're going to say the ball is right now dropped. What's the one force acting on it when it's first dropped? Gravity, the force of gravity, which is going to stay the same the entire time, right? Yeah. The force of gravity just equals the object's mass times the acceleration of gravity, which, as an aside, lowercase g acceleration of gravity equals what always on Earth's surface? 9.81 meters per second squared. Anyway, so this object will have a certain force of gravity that will not change the entire time. Because it has a net force acting on it, what will it be doing as it falls? Like, how will its motion change as it falls? It'll speed up the entire time. Every second that goes by, it's going to go 9.81 meters per second squared faster than it did the second before, right? So it's going to be speeding up as it goes down. As it goes faster and faster and faster, though, the air resistance is going to build up. So we're going to have also a force of gravity, or still the force of gravity, but eventually we're going to have an air resistance too, F sub A for air resistance. As it goes faster and faster, the air resistance is going to do what? increase. Is the force of gravity going to change? No, the force of gravity is going to stay the same. So eventually what's going to happen?
The air resistance is going to balance out.
Exactly. The air resistance is going to balance out the force of gravity. And at this point, what is the net force on it? Net force equals 0. Net force equals 0. Does that mean the object has stopped? Be very careful. No, the object didn't stop. It just doesn't have any... It has no net force and therefore no... What's the other thing? It's no longer accelerating. It's no longer accelerating. Does that mean it has stopped midair? No. It is going to continue moving how?
Constant speed.
Yep. Continue at a constant, not just speed, but it also has a constant direction, so a constant velocity. And we call this velocity, when an object's, the force of gravity acting on it balances the air resistance, we call this the terminal velocity. I know you've heard of that before. Terminal velocity. And it's really a kind of complicated equation to calculate air resistance on an object, but it depends on quite a few things. I know it depends on the density of the medium, so like how dense the air is. Since water is a lot denser than air, the terminal velocity is reached very quickly in water. It also depends on the cross-sectional area, like what wideness of the surface it presents to the air, and so that's why a parachute works. It depends on the velocity of the object, as we talked about. There's a lot of things. The air resistance equation is really quite complicated, but effectively, for us, if everything else stays the same, as the object goes faster, its air resistance increases, eventually reaching a point where there's balanced forces only, and from then on it will just fall at a constant rate. That's why, where did this come from? Was that me? I think it was me. Hopefully I don't get coronavirus from this demonstration, but that's why if we have this little thing, this is kind of a nasty looking Kleenex. I used it to wipe off my cup earlier, I've now remembered. How long does it take for this to reach terminal velocity? None, right? Basically, as soon as I drop it, it's at terminal velocity. It just falls at a constant rate from there on down. Same mass, right? Remember we talked about how mass does not influence how fast a thing falls. Same mass, it probably still hadn't reached terminal velocity by the time it got to the bottom, right? Because it has a different cross-sectional area, and therefore a different air resistance. Do you have questions about terminal velocity? Questions about pressure? Questions about friction? That wasn't a word. Questions about friction? Questions about force in general? Okay, I trust you. Ian. Bye. That should be the entire chapter. I mean, obviously we didn't touch on every single thing. Well, no, I did touch on every single thing, but I didn't go through and read the book to you. So you still have to read the book. You have a chapter review to do. Tomorrow we're going to do the same thing for chapter 6. If you have any questions, let me know, okay? I'm not giving up. I'm just coming to sit down to put this video up for Jada and Hadley. If you have questions, please let me know. Hopefully this doesn't